Welcome to section 9.7, Functions of a Random Variable. At the end of this section, we should be able to answer these questions. What is a binomial experiment? What is a probability distribution? How is the binomial probability distribution related to the expansion of a binomial raised to a power, i.e. a plus b to the n? What is the binomial formula for calculating the probability of a certain number of successes out of a certain number of trials? How can we use our calculators to help us determine and graph a binomial probability or a binomial probability distribution? Well, let's look at an example. Suppose you have a bent coin. The probability of the coin landing heads up is 0.4. What is the probability of 2 heads and 3 tails in 5 tosses? Now notice that this question is not saying 2 heads and then 3 tails, but it's any combination of 2 heads and 3 tails in 5 tosses. So we're going to look at this question in 2 parts. First, how many ways can you end up with 2 heads and 3 tails? Well, if I think about it, I could first have a head, and then another head, and then 3 tails. After I've chosen the first 2 heads, the next 3 have to be tails. Or I could have a head, and then a tail, and another tail, and then a head, and finally a 3rd tail. But either way, after I've had 2 heads, that leaves the other 3 to be tails. Out of the 5, 2 are chosen to be heads. If I think of it in those terms, I'm choosing 2 of the 5 to be heads. And there are 10 different ways, if we check with our calculator or use our combination formula, to have that scenario occur. What are those 10 different ways? Well, fortunately for you, I have detailed them. Here they are. For example, the first way it could happen is to have the 2 heads and then the 3 tails. Or I could have heads, tails, heads, then tails, tails. So with these 10 different ways, what's the probability of any one of these permutations occurring? Well, if I look at the first possible way that they could occur, that would mean that I had a head thrown on the first throw, and the probability of that happening is 0.4. And then I had a head on the second throw. So the first throw and the second throw are heads, and the 3rd throw is a tail, so the probability there is 0.6, and that would occur for the 4th and the 5th throw. Notice how all of these things happen, and so I multiply. And if you look at all these other possible outcomes, those same 5 numbers will occur in each scenario. So the probability for one of these outcomes to occur would be 0.4 squared times 0.6 cubed. So to determine the overall probability, that would mean that either the first outcome occurred, heads, heads, tails, 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 or the second outcome occurred, or the 3rd, etc., for all 10. So since each one of these calculations comes up with the same value, I could add all 10 of them together to find the overall probability for this scenario. So my probability would be 10 times the 0.4 squared times 0.6 cubed. So what was the process? How could we use this thought process to come up with a general formula or strategy for dealing with any one of these scenarios where we have 2 possible outcomes with differing probabilities for the outcomes? Well, if you look at our formula up here, the 10 times 0.4 squared times 0.6 cubed, and we describe what each of those values represents, we can see that the first number, the 10, comes from the number of trials which in this case was 5 trials. C, the number of successes, which in this case was 2 heads. So that 10 came from 5C2. We took that 10 and we multiplied by 0.4 squared. 0.4 squared comes from the values 0.4, which was the probability of success, and then we raised that, we squared it, because that was the number of successes in the question. We next multiplied again by the 0.6 cubed, where the 0.6 was the probability of failure, and we raised it, in this case, to the third power, which was the number of failures. So if we follow this formula, the number of trials, C, number of successes, times the probability of success raised to the number of successes, times the probability of failure raised to the number of failures, we'll find the probability of a certain number of successes out of a certain number of trials, as long as we know the probability of success. The situation we just described is known as a binomial experiment, where we have a random experiment consisting of the same action over and over again, and that action has only 2 possible results. E will be one of the 2 possible results for our notation. And we'll let A be the probability that event E occurs in any one repetition, and B be the probability that event E does not occur in any one repetition. So if A is the probability that the event occurs and B is the probability that the event does not occur, then B must be equal to 1 minus A. B is the complementary event to A, as we discussed in the last section. If we use this notation and we let X be the number of times event E occurs in n repetitions, for example, 2 heads in 5 throws of a bent coin, then the formula that we came up with looks like this. The probability that we have a certain number of successes is NCX, where N is the number of trials and X is the number of successes, times A to the X, where A is the probability of success, X again is the number of successes, times B, which is the number of failures, raised to the n minus x, which would be the number of failures. So that's the same formula we came up with here in the coin toss. Number of trials, C, number of successes, times the probability of success raised to the number of successes, times the probability of failure raised to the number of failures. Note that the probability of success plus the probability of failure has to equal 100%. Those are our only 2 possible outcomes. Now we have this note here that the P of x has the value of the term with a to the x as a factor in the binomial series. So what does that mean? Well, let's look at our experiment again, and we will say that this binomial series here for our experiment would be 0.4, the probability of success, plus 0.6, the probability of failure, or tails, raised to the 5th. Now, if I expand this binomial, I will get something that looks like the 5th row of Pascal's triangle, if we remember that. So I would have my first term times 1, so 0.4 raised to the 5th, plus 5 times 0.4 raised to the 4th, times 0.6 raised to the 1st, plus 10 times 0.4 cubed times 0.6 squared, plus 10, 0.4 squared, 0.6 cubed, plus 5 times 0.4 times 0.6 to the 4th, plus 0.6 to the 5th. If we examine each of these terms and think of them in terms of the ways to get a certain number of heads and a certain number of tails, we'll see an interesting correlation. For example, the question we asked about was 2 heads and 3 tails in any combination. And we said that that was going to be, for 2 heads and 3 tails, our formula was 5c2 times the probability of getting heads raised to the number of heads times the probability of tails raised to the number of tails. And 5c2, as we saw, was 10. There were 10 different ways for that to happen. So I have 10 times 0.4 squared times 0.6 cubed, which just happens to be a term in this expansion. And if I thought about the other terms, if I were going to get 5 heads, the probability of that happening would be 5c5 times the probability of getting a head raised to the 5th times the probability of failure raised to the 0, which turns out to be there's only one way to choose 5 out of 5 times 0.4 to the 5th times 1, which is just 0.4 to the 5th, which is our first term in our binomial expansion.